just turn it into a registrar?
I think just give it back to me because she told me to bring it up there
with the package?
Yeah.
Okay. All right, I'll make up something nice then. I'm sorry. Okay. Okay, let's get this. Okay, I do want to make a couple of announcements. I am recording now. I want to make a couple of announcements. I guess I'll do them in this order. The first mini-term ended last week. Like I said, I'm working on getting those grades in today. Second mini-term basically starts today. So some of the weekend was midterm, okay? Now, this week, if you look at the academic calendar on the website and look at this week, it'll say midterm progress reports due. Okay. Sometimes they forget to open that for us to do, and if they don't open it, I don't mess with it. But other times they will remember to open them, and then they'll say, you need to get these in. Okay. Now, what does that mean? They want to know students who are failing or have a D at midterm. In other words, students that might need some attention. I think all of you are high enough students. You probably will get attention on your own. You know, you'll take care of things. But just to let you know, only 2 of you 4 have, and of the 6 total in the class, have turned in a paper. And 0 of the 6 in the class have done your first test. I'd like to have a score by the end of this week in case they do open it up and say, I've got to have something in. That way I don't have to say, yeah, this person's failing at midterm, because if I don't have any grades, I have to say you're failing. So try to get me, if you haven't got the paper in already, if you have, good for you. If you haven't, try to get either the paper or the test done by the end of this week. Now, there's a good chance they won't open it up, and then it's no sweat, but I don't know that that's going to happen. So just to cover our bases, and if you're in chemistry, your acids too. Never mind, I didn't say that, did I? Okay, let's get that covered. Okay, good deal. Okay, so I was recording that too, by the way. Okay, the second feature of the fact that we are in the second mini-term, beginning today, and this won't really go into effect till tomorrow. The first mini-term, I had a physical science class that started at 12:30 on Tuesday, Thursdays. So my office hours on Tuesday, Thursdays were 10:45 until 12:30. This mini-term, I've got another physical science class, but it starts later, 1:15. So that expanded my office hours on Tuesday, Thursday to 10:45 to 1:15, which gives me a little more time in the office. So if you need to see me then, those are good times to come do it. Also gives me more time to work on some stuff like your thing. Okay. The bad news on that, and it isn't for you, but for me, I stay here till 5:45 then on those days, probably closer to 6 o'clock. So, but I can live with that. Done it before. Okay. And the third, and this is the fun one. Have y'all heard of the movie Hidden Figures? Yay or nay? Have you seen it yet? If you want to see it, UAB is having a showing of it at the UAB Hill Student Center, brand new building, okay, in the Alumni Theater. I can't tell you where it is, but I'm sure they have directions in the building. And that'll be this Wednesday, March the 8th, 5 o'clock in the afternoon. Can't do it, you got physics, right? Okay, but if you can, it should, I mean, I've seen the movie. It is an amazing story and a very well done movie, okay? It won some Oscars, I don't remember how many or something, but it did. It was nominated for quite a few, okay? UAB has invited us to come and participate. From what I understand, there will be at least one or maybe more cast members there. I don't know if it's one of the big stars or not, but they said that a student was telling me about it this morning. I haven't seen anything officially, but he said that. I was amazed to hear it. Okay, now do any of you have any? Okay, there may be a vehicle leaving from one of the 2 campuses. I don't know for sure. I just found out this morning, so I haven't been able to talk with anyone. If you need transportation, I should know by Wednesday, or you can contact me sooner. Okay? if you're driving yourself, does everybody know how to find the UAB Hill Student Center? Okay. If you have doubt, I can give you general directions. Do you know any landmark on UAB campus that I could give you directions from? No. Okay, you know how to get UAB campus. Okay. You know the main drag is University Avenue. You know that one? Okay. This is on University Avenue. Now, University Avenue on the east end is mostly medical. Okay? Medical research. There's the Eye Foundation Hospital. There's the VA Hospital. All right there. You know where those are? You do? Okay. If you continue west on University, past the Eye Foundation Hospital, I think the very next building, there's going to be a big parking lot, but the very next building on that same side on the right, it will be Hill University Center. Big, brand new looking building, several stories high, lots of glass, really modern looking. That's the Hill University Center, Student Center. The bad news is where to find parking. Okay? UAB parking is always difficult. Okay, now here's what I'm going to do if I get to go to it. I'm going to drive the UAB campus. I'll probably be coming in from the west side. Okay? I'll probably come in from 4th Avenue. If you get off the interstate and go 65 south, if you know what I'm talking about, 65 south, 4th Avenue south exit. Okay? Coming from 2059, you hang a right, get on 65 south, you have 6th Avenue north, then the next exit is 4th Avenue south. I get off there, and it loops around and goes back under the interstate, and as I'm driving 4th Avenue south, I'll start looking for parking places there. If I don't see any there, I'll move one further south to 5th Avenue south, I'll look there, then 6th Avenue south. I don't think there's much chance of looking on 7th Avenue or 8th Avenue. But somewhere on 4th, 5th, or 6th, especially that time of day, you should be able to get a parking place. Okay? Now, if you are too close to this end, if you're down near the Bartow Arena, do y'all know where that is? Okay? You're too far west, but you can walk there. Okay? But if you get to the Bartow Arena, just keep walking east. On University, you'll see it on the left. Okay? Makes sense? If you get to Eye Foundation Hospital and VA Hospital, you've gone too far. Go back west. Okay? Great movie. As far as I know, it's free. It should be worth the trip. Okay. All right. Any questions on that before I go any further? Okay. According to my mark, we're in section 2.5. Chapter 2 is first order differential equations. 2.5 is solutions by substitutions. Okay. Sounds like, integration, okay? And you might find it not that different. But let's take a look and see. Okay. I think we talked about substitutions, so we're down to homogeneous equations. A function f possesses the property, if a function f possesses this property, that, oh goodness, let me get on my dark color. Okay, here we go. F of tx, ty is equal to, goodness, I can't even read that. What's the superscript there over? Oh, that's an alpha. That's what it is. T to the alpha power times f of xy. Okay, boy, that was not that easy for my old eyes to read. For some real number, if I just read further. Then f is said to be a homogeneous function of degree alpha. This implies it's a homogeneous Oh, and by the way, alpha a real number. Could be positive, negative, fraction, decimal, rational, irrational, any real number. Then this implies that f is a homogeneous function of degree alpha. Okay. Now that's a weird way to express it in my mind. Okay? But here's an example. F of xy could be x cubed plus y cubed. Okay? What kind, does that fit the bill here? Yeah. That, what would you say its degree would be? 3. That would be a homogeneous function of degree 3. Okay? And here's why. Here's the requirement, okay? So then our f of tx, ty would equal t x cubed plus t y cubed, okay, which is equal to t cubed times x cubed plus y cubed. Okay, strange way to go about doing things, and that would be t cubed of f of xy. Okay, because your f of xy is x cubed plus y cubed. So if you can multiply t times thing, then f of tx, ty would be t cubed x cubed plus t cubed y cubed, because that's the definition of f. You can factor out the t cubed and leave your x cubed plus y cubed. That's your f, okay? And that would be t cubed times f of xy. So sure enough, that is a function of xy. Now, whereas f of xy is equal to x cubed plus y cubed plus 1, is that a homogeneous function? No, because if you tried to do the same thing we did before, tx, ty, this would be t cubed x cubed plus t cubed y cubed plus y, okay? Then you can't factor out a t cubed because of that 1 there, okay? So that would not be a homogeneous function, okay? So this, to me, is a slightly different definition from the one we're used to seeing, okay? But that is. Now, a first-order differential equation in differential form, let me start this in a new page because I'm not sure we'll have enough room to write everything we need here because this is sort of new. A first-order differential equation in this form, this looks familiar, doesn't it? M of xy dx plus n of xy dy is equal to 0. Okay? That's said to be homogeneous. Okay? Now, they say here the word homogeneous does not mean the same thing as it did in the remarks at the end of section 2.3, which I doubt if we went over. Recall that a linear first-order differential equation, ax y prime plus a1x y prime plus a0 xy equal g of x is homogeneous only when g of x is 0. Okay? This is a slightly different approach to homogeneous, and it's not the same meaning. So like I said before, these don't seem to be consistent. Sorry about that. They use the same word for various concepts. This is homogeneous because the whole thing is equal to 0. Okay? But, I'm sorry, it's only homogeneous if both the coefficients m and n are homogeneous functions of the same degree. Okay? Go back up to the earlier thing. They must be of the same degree. In other words, if this m of tx, ty, same rule we had before, is equal to some t alpha, t to the alpha, of m of xy, and n of tx, ty is equal to t to the alpha of n of xy. If both of those are true, and that's the same degree, those alphas are the same in both cases, then these two functions are homogeneous functions of degree n, and then you can say, this is sort of a stretch here, okay? But you can say m of xy, and they it's not intuitively obvious this is true, but they're saying it is. We can also write this as x to the alpha times m of 1y. I'm sorry, it's not a plus, it's an and it came out of plus. And you can write n. Yuck, I can't write. Okay. N of xy is equal to, I'm sorry, I'm saying this is not right because I didn't write down the right variable here. 1u, n of xy is equal to x to the alpha times n of 1u, okay, where u is equal to y over x. Okay. Now, you might say, justifiably so, what? Or why? Or how? Okay. Well, hopefully they'll do a little bit better of describing this later. But if x's and y's are related with the t's here in this manner, okay, then you can kind of divide the y by the x and in some senses kind of cancel out the t dependency, but maybe not completely. What's left is, this is sort of a gross way to look at it, is related to this function u, okay? And it just is not intuitively obvious from here that that leads to this at all, okay? But it does, okay? Now, not only that, you can do it the other way. M of xy is equal to y to the alpha times m of u. I think they still use, no, they use v now, okay, because it is a different function. I thought they were going to use, well, it didn't. Nope, yuck. Okay. v1 and n of xy is equal to y to the alpha n of v1. This time where v is equal to x over y. Yeah. Okay. And again, it doesn't seem like that naturally flows from this, but it sort of makes sense. If this is true, then that would kind of be true too. But where is the rationale that any of it's true? Right now, you have to sort of take its word for it, okay? Now, it says, see problem 31 at the end of this section. I'm sure that's going to be a big help, okay, to me. Properties 2 and 3, the last two we just put up here, suggest that substitutes can be used to solve a homogeneous differential equation, specifically either of the substitutions. Now, if you go back to this one, yeah. Okay. This is u is equal to y over x. That goes with the top one here. And b is equal to x over y. That goes with the bottom one here. Okay. I just didn't leave enough room to get the y is equal to u is equal to y to the x. That's a u. That's a y. That's a b, and that's an x. Okay. Sorry about the sloppy handwriting. And thanks for making fun of me, by the way. Okay. Now, all right. Let's take this expression and rewrite that ever so slightly, that y is equal to ux, right? And similarly, we could take this one and say x is equal to vy. Okay? Now, with that in mind, kinda, okay, up here, let's take the first case, this one. This would be m of t x, comma, make sure that's what I want to do, t u x, okay? Those y's is this, and the other, okay? And that would be t to the alpha, mxy, and n of this would be t alpha n, and keep that same substitution. X, comma, tx, no, x. Here is tx. Here, and here is t x, tux. This would be t to the alpha m of xu, I think it is. Yeah. If you follow that through that way, putting these in instead of the y, and going from there, and then later dividing out the x, that's where this comes from. You know, follow that all the way through, and then you can pull out, rather than t, pull out your x to the alpha, and that leaves a 1 here in u. Or using this one, it divides out and leaves a v of 1. Okay, that's a lot of arm waving there. Okay, but anyway, here's some more. I wish I had more room on the screen. What I think I'll do is erase our first line, which is kind of important, but I just need the room here. Here's the other condition. I should have written this before I started talking about it there. The m of xy is equal to y to the alpha m of v1 and n of xy is equal to y to the alpha n of v1. Oh, I'm sorry, I already had that. I had written that down. Yeah, I'm sorry, I already wrote that. Sorry about that. Duplication. Yeah, I'm sorry, I was already on to the next. Okay. So let's can that, because I thought this is stuff I've already done. Okay. That was written at the bottom, sorry. I thought I flipped over a page. Okay. Now, yeah, that's where we left off. Where U and V are new dependent variables, will reduce the homogeneous equation to a separable first-order differential equation, which we know how to do. Okay? To show this, observe that the consequence of this equation, number 2, that's this one here. Okay? A homogeneous equation, like I just erased, the one I should have kept up there, can be rewritten like this, or yeah, okay. Now, let's go back to this right here. Okay? This isn't a stretch. Okay? I hope not. dy is equal to u, see, that should be a partial of y is equal to u partial of x, or dx, sorry, that should be the dx, plus x du. Yeah. All right. That's the equation on page 72. There's not a numbered equation right above it, but there is a couple of equations there. dy, and that they write it as a dy, not a partial. Seems like it should be a partial, but we'll take their word for it that it's not. Okay. And this isn't a partial either, so let's see if I can do it. Okay. Okay. All right. So this equation leads to that. Okay. And if you go through, there's a whole series, 3 lines of rather bizarre looking combinations here, but it's showing how you separate the variables out. The x dx over dx on one, and then the everything with u's alone on the other. Okay? At that point, we offer the same advice as in the previous section. Do not memorize anything here, especially that last formula. Rather, work through the procedure each time. The proof that any substitution, that the substitution y is equal to x equal vy and dx equal v dx, dy plus y dv also lead to separable equation, follows an analogous manner from number 3. So all that aside, let's actually do it. To me, this book can make sometimes rather straightforward seeming concepts really muddy, okay? I'm not saying always, but sometimes it is. So here's the situation. So here we have this equation. X squared plus y squared dx plus y squared, x squared minus xy dy is equal to 0. Equal to 0 looks like it has promises to be a homogeneous equation, but we've got a ways to go before we can get there. Okay? Now, if you look at this as your m of xy, and this is your n of xy, okay? it shows you those coefficients are homogeneous functions of degree 2. Okay? Both of those are. Okay? Now, what do we mean by that? Let's do one of the substitutions we just did. Let, and I believe it was, let's do this one first. Y is equal to ux. Let's make that substitution into those forms. Okay? What does this give you? This gives you x squared plus u squared x squared dx plus, plugging the same thing here, x squared minus x times ux, that's what your y is, dy, need another parenthesis there, equal to 0. Yuck. Okay. Now, this has an x squared in it, 1 plus u squared dx, plus, this has an x squared in it, that'd be 1 minus u dy is equal to 0. Okay? Both of those have x squareds in it, right? So you could factor out an x squared there. Now let me not get too carried away here. And if I'm not mistaken, yeah. Okay. We got that one other thing to put in. All right. From here, this produces dy is equal to, you tell me, basically a product rule type thing. What does that give you? If u is equal to xy, that's our substitution. Dy would be y is equal to ux. What would dy be? Product rule. U dx plus x du. Got it. Okay. Now, since we plugged in what y was here, let's plug in what dy is down here. So this stays the same. X squared times 1 plus u squared dx plus x squared times 1 minus u. Yuck! I say u and write y. I don't know where the old gray cells are, but they're sure not functioning well today. Okay, 1 minus u, and instead of, this is a dy, I don't know why that became a du. Okay, duh. The dy is u dx plus x dy. Okay. Right here?
Yeah, I did.
Okay, this is x squared minus x times u times x.
Yes.
So that's the x squared there.
Yeah.
Okay, so x squared here, x squared there. Factor that out. That leaves you 1 from here. Factor out x squared there. You just get a minus u. Right? I didn't write the intermediate stuff. I could have written x squared minus x squared u. Here. Factor out x squared. What's that?
It's not plus x dxu.
X dxu.
Yeah, like u dx plus x.
Okay, where? What line? This.
That's
This.
go to the end.
Okay. X squared 1 plus x squared.
I thought we were just substituting.
Huh?
I said I thought we were just substituting. When we plugged in the dy, the last.
Yeah, but that only goes here.
last piece should be DU, right there above your finger.
Oh, that's a DU. Yeah, it was. I wrote a Y and then wrote a U on top of it, but didn't erase my Y. Yeah. Is that what you're talking about?
Yeah.
Okay, sorry. Yeah. I just hadn't gotten to erase the Y yet. Okay. And that's equal to 0. Okay, we still got miles to go before we sleep. Okay, let's see what we got. X squared times 1 minus U squared. My U's and Y's are having difficulty today. Dx plus X squared times 1 minus U. Well, let's see. Goodness gracious. Let me back off a little. Okay. Let's start with the x squared. X squared times 1 times u times dx. That's x squared u dx minus x squared u squared dx. That's x squared times a minus 1 u times u dx. Plus, it's driving me nuts, x cubed. I'm going to leave this as 1 minus u. I could have done that before. Yuck! Du. So let me go back and combine these two terms here. I thought it would be, I would need to separate them, but I don't think it's necessary. So let me let's make this x squared u times 1 minus u dx plus x cubed times 1. Yeah, I think that'll be maybe a little cleaner. Okay? But look at this. Let's do these two together, and what do we have? Common factors of x squared, and this is a 1 minus u times 1 plus u, right? I don't know if that helps any, but they have a common factor of 1 minus u. So 1 minus u times one plus u I factored out the common factors there. I have a 1 plus u from here plus u from here, right, dx. Okay, yuck, plus x cubed times 1 minus u du. Okay, these are all equal to 0. I forgot to write that. Okay, now this gives us a 1 plus 2u dx. All right. Oh my word. Okay. So let's see what we got. X squared times 1 plus u dx plus x cubed times 1 minus u du equals 0. Now, somehow they lost a term there, didn't they? Or did I throw an extra one in here? Okay. I seem to have an extra 1 minus u somewhere here. Okay, let me back up. X squared plus u squared. Okay, this line right here. X squared plus u squared dx minus x squared minus u. No, minus ux squared. I've got it there. Okay, but instead of that, x squared, they put it as minus ux squared. I wrote it separately. And dy, but instead of dy, they put in u dx plus x du. Okay? Oh no, goodness gracious. I see where I messed up. Right here. Oh, I messed up a lot, didn't I? Y'all should have caught me on this. Okay. That's a 1 plus u squared. That's x squared times 1 plus u squared dx. Plus x squared u times 1 minus u dx plus x cubed times 1 minus u du. Okay, let's erase this next line because I've kind of botched that one up. Okay, now, let's make sure we're at the same thing. X squared times 1 plus u. Now, I've got a u squared there. Okay, I think this is what happened. Okay, let's combine these things together. Factor out the du. Okay, factor out the x squared and the dx. Okay, and that'd be x squared dx times 1 plus u squared plus u minus u squared. That's it. Okay. And plus u squared minus u squared add to 0. That's where you get the factor of 1 plus u. Okay. Plus x cubed times 1 minus u du equals 0. So now I need to go to the top and start over again because I'm running out of room rapidly at the bottom. Okay, so let's erase this, and hopefully I will not need it again. If so, I'm in deep trouble. Okay, I just don't have enough board here. Okay, so let's get the things together. This is x squared times 1 plus u times dx plus x cubed times 1 minus u du equals 0. That's what we have, and that's what they have here. X squared times 1 plus x dx plus x cubed times 1 minus u du is equal to 0. All right, so what we're going to do is separate variables. Okay, so here we'll divide out a 1 plus u. So we'll have to divide it out over here, 1 plus u. And here we'll divide out an x cubed. And over here divide out an x cubed. Okay? So these go out here, these go out there. So now our differential equation looks like this. x, oh wait, x squared, and 2 of those x's go out here. Okay, which leaves us dx over x, right, plus, goodness gracious, this thing's aggravating, 1 minus u over 1 plus u du. And that's equal to 0. Okay, so there's our differential equation. And that, by the way, is what they have here. Then they do something that looks to be really strange, but it really isn't. This one here, they split this into a 1 over 1 plus u minus u over 1 plus u du. Okay? Now, that's not how they do it. That should produce what we, oh, no, sorry. Let's add a u here and subtract a u there. Okay. Yeah, that does it for us, I think. No, the sign's wrong. Let me back up and try that one again. Okay. Okay. I'm going to do it a slightly easier way. I hope that it won't be as confusing here. Okay, 1 minus u over 1 plus u du. That's what we have. That term alone, what I'm going to do here, and this looks like a really shady thing to do. Just remember what this is, 1 minus u. Remember that, okay? 1 minus u. Okay? I just separate it a little bit. So what I'm going to do here is put in a plus u here and another minus u here. That hasn't changed it, has it? May look different, but it really didn't change it. Just added a u and subtracted a u. Now this is the one I expand to be a 1 plus u over 1 plus u minus 2u over 1 plus u. Now, what I can't figure out is how they got the sign to change. What I've done is correct, but it's the, oh, no. It should be the same thing. Let's try it the way they said. They said by long division. So let's go back to this one. Well, let me erase all these. I can't, to myself, justify why these aren't coming out the same, but they should. Okay, sorry about this. Okay, they should come out the same, but so far they're not. Let's see if they do better when they do it this way. They say do long division. Okay? Now, most of the time we don't do our division this way, but let's do it. 1 plus u into 1 minus u. Usually we turn them around. In fact, I think I got to turn them around. Okay? Let's turn those around. Make that u minus, okay. Now I think I see where it comes from. Okay. let's do this. U plus 1 into U minus 1. Now realize this is the negative of what we got here. So really what I want to do here is bring out a minus sign. Okay. I know this is it seems like sleight of hand, but it's not. This will be U minus 1 over U plus 1. See, I pulled out the minus sign. Here it's 1 minus U over 1 plus U with a plus. So I'm going to pull out a minus sign and make it minus U minus 1 over U plus 1. Swapping these don't matter, but swapping that you need the minus sign. Okay? You buy that? Okay. Now, so let's do the long division. This is strange but true. U will go into U one time, right? Multiply, you get U plus 1. Subtract, these go out, and let's change signs and add. So this will be a minus 2. So that would be 1 minus 2 over U plus 1. Now, they still have the wrong signs, and I don't know under what justification. I've done it 2 different ways, and both ways work the way I say they are going to, and not the way they say. Okay? And I do not know how they got their minus there. Okay? The minus with the 1 and the plus with the 2 over U plus 1. I've done it 2 different ways, and both ways come out this way. So I'm convinced that's true. And I can't see how they botched it up. Okay? But let's at least leave it alone. Okay? And do the integration. All right. Now we're probably going to need some of this, but I'm going to erase it. I'll refer to it in the book if I need to come back and get it. Okay? I know I'm going to need that later. Okay? Well, let's do the integration. But I have the minus in front. That's what changes it. That makes it minus 1 plus 2. Yeah, that's where it comes from. Okay. I admit defeat. Okay. This does become this, but then the minus sign changes it around. Okay? So we're going to integrate those 2. I'm going to rewrite them. Dx over x minus 1 plus 2 over 1 plus u I don't like the way they do this, but I'll do it the same way they do. Du. Okay. It's equal to 0. Now, I don't know why they switch sides. It doesn't really matter. Okay. So I'm going to erase some more. I don't think I'll need that line necessarily, but the line before I'm pretty sure I'll need. Okay. Okay. Now we're going to integrate. And what I would like to do is move that to the other side and integrate there, but we're okay here. So what we have here is antiderivative of dx over x log x, right? ln x. Okay. Now integrate this one. That's not too bad either. This will be a minus u plus 2 times natural log of 1 plus u is equal to some constant c. Okay? So they start off with minus u plus 2 natural log of 1 plus u plus log x, and this really should have this. Now, rather than saying is equal to c, they made it log c. And there's a reason for that. Huh? Okay, what are you talking? From here to here. Is that right? This one? This one? No, that's a U. Those are U's. Yeah. There's no N's in it yet, anywhere. My U's look like N. Sorry about that.
So this second row that is log x, second row.
Okay.
That's log x minus u plus 2 log
1 plus U. And then rather than saying plus C, they put log of absolute value of C. Now there's a reason for that, and it's not probably intuitively obvious yet, okay? But we'll deal with it, okay? Now, before we do anything else, and this is where I said I would need it, let's go back to where we came from. Remember, y is equal to ux. Remember, that's where that was the substitution we made. So that makes u equal y over x. All right? So then this will be log absolute value of x minus y over x, that's the u, plus 2 times the log of absolute value 1 plus y over x is equal to log c. Still not clear why we have that in there, but we can live with it for now. Okay, now let's take this one in here and clean that up a little bit. Let's make this x over x plus there, and that would make this log of x plus y over x. Okay, so let's change this to x plus y over x. Okay. Now, they didn't do that. Okay. Sorry about that. Well, they sure to do in the next sentence, in the next line. Okay. Okay, I'm going to have to erase another line here to get things to print. Okay. All right. So a little review here. Minus y over x plus 2 times, and they didn't change this, but I did, plus that equal log c. Okay. Using the properties of logarithms. Now, here's where this comes into play. I don't know if you remember this rule. This thing right here, okay, is going to be, just this part here, is going to be log absolute value x plus y squared over x squared. You remember that? That n times the log is the log of the thing to the nth power. So the n here is 2, that n. Okay. And that would give you this. Okay? That leaves you there. Now, I can drop the absolute value bars because everything's squared. You buy that? No matter what values they are, you're squaring them. They're the, okay? So there's one other law of logarithms that I'm going to pull into play here. Oops, did the wrong thing. Okay, and that's this one. Okay, this is the same as log x plus y squared minus log of x squared, right? The log of a quotient is the difference of the logs. You remember that one? Whether you do or not, it's true. And then I'll go back and make this minus 2 log x. Okay? And then I guess I need to go back to absolute value. But here we have a log x, and here we have a minus 2 log x. So that's going to be minus log x minus y over x plus log of x plus y squared, I don't need the absolute value there, is equal to the log of absolute value c. Okay, so let's see what we have here now. Here's our log of x plus y squared, okay? Now, you got a minus log x here and a minus log x here. That's a minus log of log c there. That would be a minus times a log of cx. And, okay, one more rule of all logarithms here. Yuck. Okay. All right, watch this slide. I'm going to erase another row. I probably should erase everything at the bottom. I'm just afraid I'll need something else. I erased something down there, so that's probably a bad sign. Okay. What I'm going to do is subtract this from both sides and add that to both sides. It's a minus. Oh, okay, I thought you had a question. Log absolute value x minus log c, absolute value c, plus log of x plus y squared is equal to y over x. Okay. I think I'll erase another line. Goodness gracious, this just keeps on trucking, doesn't it? I'm going to erase it all. Goodness gracious, I'm tired of it. One at a time. Okay. Here's another rule of logarithms. If you factored out the minus sign, that'd be log of x times log c. Plus log c. Factor out the minus sign. Well, the log of the sum is the log of the sum of two logs is a log of a product. Okay? So this will be a minus log of absolute value cx plus the log of x plus y squared is equal to y over x. Okay? But then this is a minus. You can put it underneath the other one. So this would then be the same as the log, natural log of. Now this time you have to put the absolute value bars back in. X plus y squared over cx. The reason is that now when you're dividing, if either of these are negative, even though that's guaranteed to be positive, then that makes the whole thing negative, so you've got to make sure it never becomes negative. There's your answer, okay, or at least the first step in your answer. Log of absolute value x plus y squared over cx is equal to y over x. Right there, I wrote them in different order. Or, if you want, another way to look at it is take the e of both sides, e to the this and e to the that, and that would give you e of a log. These go out, and that gives you x plus y squared over cx. And notice you can drop the absolute value now because exponentials are defined everywhere. Goodness, my eyes hurt. And that's equal to e to the y over x. Okay. Now, one more thing you can do, multiply both sides of the equation by cx. And that gives you x plus y squared is equal to cx e to the y over x. What a solution. Okay? It's certainly nothing that you can separate variables on your solution, but we did separate variables to get here. And this is the final form I think they leave it with. Okay? Boy, what a pain. Okay? That was way too long of a problem. But you saw in there all the elements. Now, I just got a dumb question here. Oh, there it is. Never mind. We will begin next time with Bernoulli's equation at the top of page 73. We didn't get that far today, but we almost finished the section. This is one more. So you can do any of the odds, I think 1 through 9. I think you can do any of the odds 11 through 13, or either 11 or 13 or both if you choose. And the next ones are Bernoulli equations, so since we haven't done those, we'll hold off on those till later. Okay? Goodness gracious. What a pain. All right. Frankly, I don't know if I ever fiddle around with this one. I guess we do sometimes when you're, if you see that it's something easy to work, then do it. But a lot of times this is just, well, try those two. Either u is equal, let's see, y is equal to ux or x equal, or v is equal, no, x equal vy. Try those and see if that substitution works. And if it does, you got it. Usually a solution. All right. Good deal. We will see you